Thank you very much. Hi, everyone. So let's get started. This is joint work with Doad Kamal here and Ori Lav from Tel Aviv University, where I'm from. So our goal in this work is to fit short-stay concurrency on equal footing with other semantic models of computational effects, such as global state, input-output, abort, all sorts of effects that you see. So one of these is concurrency. So we want to use the same standard algebraic effects approach that has been successfully used for these other effects, in which we define a denotational semantics over a monad representing an equational theory. And formally, we go the other way around from bottom to top. We'll see that later. So why use this approach? What's so good about it? First off, like any denotational semantics, it's compositional by nature. Concurrency semantics is known for not being compositional, so that would be good in this case in particular. We get higher order functions out of the box in this approach. We've got uniformity, meaning that we have general results for all sorts of algebraic effects that we can apply. And even if they don't apply, we have proof techniques that are usual in this approach. Equational theories are modular. In fact, the equational theory we'll be using is a combination of different equational theories itself. Equational theories are easier to compare. So if you have a different language in semantics, such as in one work by Abadi and Plotkin, they use a similar equational theory, even though their language in semantics is different. So it makes it easier to compare. We can analyze the program behavior using our denotational semantics a bit more abstractly by using the monad equations or the equational theory. And finally, since we have a monad, it forms a bridge to implementation. If we want to implement a model checker later using the semantics, having a monad will make that easier. Okay, so there are a lot of advantages, and so let's see how this works. Now, this is just, don't get intimidated, I'll explain all this later, but just to maybe catch the ear of those that are familiar with some of this, this is what's going to happen. So we have a programming language with standard operational semantics, has higher order, and we extend it with a few constructs, assignment, dereference, and interleaving concurrency. Our denotational semantics is a standard monadic denotational semantics, and we base it on traces. And we'll see all this a bit later. And this itself is based on algebraic effects. One of these effects is non-determinism. So we have a notion of order between our denotations. And using this order, we can state a theorem that will prove adequacy that relates what we know about denotations to what we can figure out about the operational semantics of the programs. Okay, so let's start. We have two programs. One of them is a bit longer than the other. And a fact about these two programs is that they have the same execution. Okay? They're identical in that sense. So you can see an example below of how they execute. They both take the state 101 to 101, for example. But does this mean that these two programs are interchangeable? So if you plug each of them inside a larger program, will you still get the same operational behavior? If you only consider sequential contexts, then it happens that they will. For example, if we run them and then dereference A, in both cases we'll get the value 1. However, if you consider concurrent contexts, then it breaks. In the longer program, you can dereference A in between the two writes to get a 0. But in the shorter program, you won't be able to get this 0. So we see that just thinking about how programs run isn't sufficient to understand them completely. Okay, depending on what context you can have. Okay, so let's go back to the sequential setting and try to understand the denotation semantics we can give in this case, and later we'll see why it doesn't work in the concurrent setting. So we have this longer program, and let's see this denotation using algebraic operators. I think it's quite intuitive. just think about what this program is doing. It's looking up B, and then updating A to the value, and then it looks up C and updating A to that value, right? And now we can start analyzing this algebraic term. For example, we update A and then look up C. Does it really matter what the order is? So in the sequential setting, it turns out that it doesn't matter. And we have an equation that tells us in the equational theory that we can commute these two operators. And we can keep going. We have two updates in sequence, so we can just throw away the first one because it's being overwritten. And now we have a lookup that's not being used anywhere, so we can just throw it away. And lo and behold, we get the denotation of the shorter of the two programs. So using adequacy for global state, the sequential setting, which is already known, we find that they are interchangeable, right? That's what we saw earlier too. So the compiler can make this optimization, which eliminates some of the state accesses, which might be expensive, so that's good for us, right? In fact, it can also optimize in the other direction. It just doesn't seem as useful. Good. Okay, so how do we extend this to short state? We need a denotation that can handle the power construct. So first of all, in order to handle this, we'll need non-determinism, right? So lookup and update won't be enough. We'll add another operator of choice. So we can handle the fact that concurrent execution isn't deterministic. And we'll add some axioms to our equational theory. Some that are just obvious of how choice behaves, and some that just say that the operators commute, like updating and then choosing is the same as choosing and then updating no matter what branch you take. And this is all known. All these equational theories are already known from before. This is just background. Okay, and now we can state adequacy for this case, which is more refined because we don't just say that when the denotations are equal, we can say when one of them is smaller than the other in the sense of the order obtained from choice. This means that we can replace in the opposite direction, right? Because replacing in the opposite directions means that we're not introducing any new results. In particular, no bugs will happen if we do this replacement. But remember the example from before. The example from before says that this can't be, because we saw that these denotations are equal. So the denotation of the longer program should be smaller than the denotation of the shorter one. But this contradicts what we saw about the execution if we had adequacy. So the point is that we can't just extend the denotations we had before. We need a new idea. Okay, we need these denotations to not be equal, right? Because that transformation shouldn't be legal. So what do? Do we invalidate equations or change the denotations? We need somehow to not have this chain of equations hold. So our approach is to change the denotations, but keep all of the equations in the theory. This way we get to keep global state. This is also just mathematically interesting to just keep all of the equations that we had. But also we'll see that we will be actually using these equations of global state later on. Just the denotations are going to be different. Just slightly. What are we going to do? We're going to once again extend our theory with a yield operator. And once again, the theory was known. It's just that how we're using it to define denotations is new. So we just add a single operator. We just add the axiom of commuting with choice. And we define from this operator a possible yield, like this. And then our denotation is almost like before. It's just that after every effect, we add a possible yield. So the intuition is that we're possibly yielding to the environment to do its own thing. Okay, so using the non-deterministic order, we can sometimes say, here we're not yielding to the environment. And this will allow us to use our global state equations just like we did before. And once again, get the denotation of the shorter program. Just notice that we're not getting inequality anymore. We're just getting a one-sided inequality, right? And this is the one that we should be getting. This is the one that is valid in the concurrent setting. It's the other direction that was problematic. Okay, so if we prove adequacy, we'll be able to justify this transformation. Great. Okay, we have a few lingering questions that we'll address in the next section. We did show one side of the inequality. but we should also be able to show that the other side doesn't hold, right? If we want adequacy to actually work. We still didn't find the denotation of par. And also, we didn't talk about the pure fragment. So you see here another two denotations that should be equal, even so they don't. Inside the program, you don't see the effects, right? M and N could have effects inside them, but this equality, what it says something about the pure fragment, right? Something that should hold no matter what the effects are in the language. Okay. So this will also be addressed later. Okay, so let's drive down the road of algebraic effects. We'll define an equational theory. We'll define a monadic model over the equational theory. We'll define denotations over the monadic model, and we'll prove that the denotations are adequate. So this is the equational theory. Now we're actually seeing it. We won't go through every equation. That's a waste of time. But just, for example, notice this one that we've used. We've also used LU commutativity. So these are the global state equations. We have non-determinism. What we've shown before was binary non-determinism. So officially, we have finite non-determinism. This will take about 20 minutes to stare at this to understand what it's doing. But believe me that it's exactly what you would expect from non-determinism, right? To kind of like behave like a set. And we state the commuting of the operators with non-determinism also yield. Again, the equational theory was already known before. Okay, let's define our model. So to define the model, I'll first need to make a quick interlude discussing traces. So we saw execution. You take a program, you have an initial state, then you run it, and you get a final state and the result of running the program. But here we're saying something a bit more refined. We're allowing the environment to change the state. That's the idea. So you take the program, you execute it partway, then the state might change, but the program remains the same. You keep executing, you allow the state to change until you reach a final value. So that's the idea of traces. So traces over X are non-empty sequences of transitions followed by a value. So this is an example of a trace over unit times values. Good. Now, we take these traces, and our model is finite sets of traces. In order to have a model, we want this model to satisfy all of the axioms of the theory of resumptions. So we need to interpret the operators, and we need to interpret the variables. For example, we interpret non-determinism as just union of sets. And we interpret yield as adding a transition that doesn't do anything. Why do we interpret it this way? Because this adds a break. Okay, so we have the same trace that we had before, but now we also have an additional break, a breaking point where we can we allow the environment to do something. That's the intuition. And we have interpretation of lookup and update. For example, for update, we take a trace in P with an updated state, and then we say that without the update, that's a trace that we have here. Notice that we're not adding a transition because we don't want to add a break. We want only yields to add breaks. And this here, the interpretation of a variable, it looks like there's a break, but there's not a break here. Okay? But between the sequence and the variable, we're not considering this to be a break. Okay, so with these interpretations, all the axioms hold. Now, let's take this model and make it into a monad by equipping it with return and bind. So return X is just the interpretation of X, and binding P to F works this way. You take a trace from P, and then you apply F to the value, and you take a trace from F of X, and then you squish them together. Okay? What do I mean by that? I mean that the final state from P needs to match the initial state from F of X, and then you get rid of that middle state, and you get your trace in the bind. Because we don't consider it to be a break here. That's why we want this to happen. This is called mumbling. That's the official lingo. You might ask, why do this? This seems arbitrary. Why did I choose to do that and not something else? So in fact, every equational theory induces a monad already. What we're doing here is finding a representation for the monad. So if this choice was really arbitrary, we wouldn't be able to prove the theorem of representation that we have. This monad T is equivalent to the monad induced by the theory of resumptions. So if we already had an induced monad, why would we bother defining a monad representation? Because it's more concrete and it will be helpful later on to define the denotations. Corollary of this theorem is soundness and completeness. So terms are equal in the theory of resumptions if and only if their interpretations are equal in the model. Okay. Now we'll define the denotations. So what are denotations? You need a well-typed term, and the denotation is a function. You need to give it is an initialization of the free variables, and you get back a semantic element. For example, the shorter program that we saw before has type unit, doesn't have free variables, so you don't need to give it anything. And what you get back is a finite set of traces over unit. Here we have one free variable, location, so you need to give it a location, and what you get back is a finite set of traces over values. So that's what denotations are. We need to define them, and you'll notice, keep this in mind, our definition is entirely compositional. Denotations of programs depend only on denotations of subparts. This is something that's inherent to denotational semantics. So let's go over the definition. Definition is in 3 parts. The first is standard. Most of the definition is standard, and it's based on work by Mogi 30 years ago. So this has long been known. These are some examples of denotations. Denotations of variables is just returning what the context says about the variable. Denotation of let binding, for example, let x equal m and n. You need the denotation of m, and then you bind it to the denotation of n, where you extend the context with the result of m. So this is how higher order gets into the picture. And denotation of pairs is denotation of the first, bind to denotation of the second, then return the pair. So that's how it works. Okay, notice nothing here depends on the programs m and n, only on their denotations. And just from this first part, we already see the equation that we asked in the lingering questions. So we have our answer. You can just, using monad laws, show that these are equal. So this would be the same no matter what effects you have. State access parts. Here we'll be using our algebraic operators. So we use lookup in the reference case and update in the assignment case. And it looks exactly like it looks in the global state, the one that's only sequential. We just add this possible yield. And if you just calculate the denotations, you'll see that they're different. So we answered our second question. Finally, how do we define the par construct? So here we're not using bind and return. We're defining a new semantic operator, semantic par, which works like this. How do you get the traces in the set semantic par between P and Q? You take tau from P and pi from Q, and you interleave the transition. So you take a transition from here, transition from there, and kind of stick them together, and that's how you get your traces. But you sometimes need to mumble them, like we saw in the bind. Sometimes you can mumble them, and sometimes you have to. So there is a formal definition of exactly what kind of interleavings you need in this set. So this is what we have here. It's defined using an inductive definition. We won't go over it because I don't have time. But if you're interested, you can ask about it later. Okay, it's rather simple. Okay. Now, adequacy. So this is the theorem that main theorem of the paper, where we just need to understand exactly what this less or equal sign means. It just means containment of sets up to giving it the same context, the denotations of m and n. And there we have it. And even the proof is, we're enjoying the fact that we're using this standard approach, because even the proof is standard. Okay, we're using a standard logical relations. We get higher order out of the box. And some of the proof, some of the definitions of the proof do need to be specific, but a lot of it doesn't need to be specific. And one concrete reward is to justify transformations without simulation. So thanks to this theorem, we don't need to think about program context. All we need to think about is their denotation, which takes care implicitly of the context. So here are some transformations that we've shown. Here's another example of a pure transformation. We don't need to think about the details of our particular semantics at all when proving standard transformations. We just use monad laws. And we'd use the same proof if we had different types of effects. So that's one nice thing. Here are two other categories of transformations that are specific. One of them is redundant access eliminations. So if you look up location, after you've written a value to the location, you can just give the value instead of looking it up. So you get rid of the lookup, the dereferencing state access. To prove this elimination, you just use algebra. So you still don't need to think about the traces. You just use mundane algebra to prove it. The last category, laws of parallelism, for example, sequencing. Here you do need to think about the traces, but again, you don't need to think about the program context. All you need to do is think about how the interleaving works. So it's still much simpler to prove this. However, unfortunately, the semantics is somewhat deficient in that we cannot prove introduction of state accesses. So this kind of transformation is useful on occasion, but we cannot prove it because we have the sort of counting issue where we count the yields. So our semantics is not fully abstract, but still, as you can see, it is useful. It's not the perfect semantics that you could hope for. Okay, a few final words. Here's a very partial related work timeline. You have Brookes coming up with the idea of sets of traces as denotations for his imperative language, concurrency. Have some work on introducing the idea of algebraic effects, global state, by Plotkin and Power, and later on equational theory of non-determinism and resumptions, some use of algebraic effects for an imperative language of concurrency, and even using monad for functional language of concurrency. So many of pieces of this work already exist, but our contribution is using the standard approach, the standard definition, standard proofs. We've algebraically justified some transformations, and an additional small perk is that our model is finite sets of traces. So this is another bridge towards implementation if we ever want to try to implement a model checker. Okay, so this was bare bone. We tried to, in the spirit of reductionism, we tried to only analyze the smallest possible language and features just to get the idea across of using the standard approach, but you could try to extend it in all sorts of ways. Right now, we're thinking about extending it the semantics of weak memory. So what we saw in the keynote talk about release acquire, that's exactly what we're thinking about. Because right now, we're just using the sequential consistency model, which is perhaps the simplest one. Okay, so that's it. Thank you very much.
Thanks, Jurgen. I guess we'll open up for questions. We have a microphone. Go around.
Oh, yeah.
Right.
I'm not using it, but
Cool. Yeah. Are there any questions? Got one over there.
Hi, thanks for the show. In your Adequacy, I see a universal multiplication of the context.
I'm sorry, I still can't hear. It's a bit difficult.
Can you hear me now?
It's not on my committee, it's for the audience, so you just need to speak on
Okay,
Yeah.
okay. So in the Adequacy,
Adequacy, yeah?
you have a universal multiplication of the contexts, right? There.
Yes.
And it's unconditional.
Yes.
That when you want to prove things about compared programs, a useful technique is, for example, reliability, where you are assuming something about the concurrent context. There is at most this much interference, right?
Mm-hmm.
How difficult is it to incorporate this kind of reasoning, conditional on the context?
Yeah, thanks for the question. So here in the possible extensions, one extension that you could make is a type and effect system, which so in the typing right now, we don't say anything about what we do or what the environment does, but you could extend it in the sense that the typing would also include what you're doing, what the environment does. And we have reasons to believe that this would work quite well, but we're not sure. We haven't actually done it. For example, we could say the environment is not allowed to read, and then you could have maybe you have an equational theory with more equations, or you just assume something about this, about what the denotation is, but we haven't done it yet. It's one possible extension we could try to do.
The idea is that the universal quantification is over type context, and so by making types richer, we can.
Yes. Yeah, that's what it would say, I think, but we haven't done it.
Another easy question, because you mentioned you don't have full abstraction. So, is there any theoretical reason why it's hard to get full abstraction, or is it just?
So other works do have full abstraction, but it was difficult. What? First order. Yeah, okay. I should mention higher order full abstraction is inherently difficult, but what I showed that even in the first order, we don't have full abstraction. And that's because of this counting issue with yield. We have tried to solve it, but didn't. We do have ideas about just using a different algebra, but then we won't have exactly global state. It will be something a bit different. We tried to keep global state, and when keeping global state, we didn't achieve full abstraction.
I guess another question is, you mentioned something about context and then about denotations, and that you don't need to know the context because you're confident of doing denotational equivalence. And from what, like maybe very naive or different context perspective, I think of context as like more limited than denotations, or denotations as the most general thing you can look at. And then like denotation of equality, right, versus contextual equivalence or something. So was it easier to look at like equality in the context of denotations rather than context or something? Like,
I'm not sure I'm answering your question, but what I tried to say is that if you don't have this adequacy theorem and you try to justify a transformation, then you need to think about all of the possible program contexts and do a sort of simulation argument and what the context would do. And you're thinking about the program itself. When you have denotations, then you have a simpler mathematical object to observe. And you just get rid of a universal quantification, which makes things easier. I'm not sure I answered the question. But,
I guess the question is thinking about denotational equality easier than thinking about contextual equality? Like
yes, I think it is. Yes, I think it's much easier. But maybe we can discuss this later because I'm not sure what you're getting at exactly. Yeah.
Hi. So you understand first order ground state, is that right?
No.
It's just right.
Okay.
Yeah.
The language is higher order, yeah.
The language is higher order, but the things you store in the state.
Oh, the store, yeah. The store is just
Have you thought about specifying that using effect handlers?
No, but maybe we should.
You should be able to define the entire language in a meta language of effect handlers, and then maybe show that the effect handler is correct. Response to your semantics.
Yeah, maybe we should, but we haven't.
So I think that was the last question.
Okay.
The next speaker. Thank you very much.